Hello, everyone. Time is 3 p.m. Let's start. Firstly, I would like to introduce myself to you briefly. This is Ulaş Taç. I am working at BİAS Mühendislik as a sales and application engineer. I am responsible for sales and after-sales support of interface products in BİAS. And before starting, on behalf of BİAS, I would like to thank you. For all to joining us today. Welcome to our first webinar with Interface Force Measurement Company. When I check the participant list, I see the different participants from the different company and the industry and academic side as well. It looks great. Thank you for joining us. We have a great content for you today. We will talking about mainly load cell basics that is named load cell theory and selection parameters. Load cell selection could be a complicated case by case. As you know, there are many type load cells and their adapters, connectors, bases or something else based on the several applications. We have received many questions from your side on this subject, and we have tried to answer them by working together. And then we decided to discuss this issue together in order to mention main parameters together. I hope it will be sufficient, both of us, end of the presentation. We will have two speakers today from Interface Company. One of them is Mr. Jeff White. You can see that. Mr. White, who is working for Interface USA as a sales director. And another one is Mr. Rob Beyl, who is working for Interface UK as a sales director. We would like to especially thank you again, both of you, for your interest and great support in Turkey markets for years. Our presentation has totally 8 parts, included question and answer sessions. During the presentation, all participants will be mute mode. If you would like to say or ask something, please write on the chat box. We will discuss on it end of the presentation with you together. All questions written on the chat box will be answered end of the webinar. So now I would like to invite Mr. Jeff and Mr. Rob to start the presentation, please. You can share your display and take the management.
Very good. Well, everyone can see my screen, load cell basics right now.
Yeah. Good.
All right. Well, appreciate everyone's attendance in this and interest in learning about interface load cells. We have a lot of good information today. A lot of basic information, but I think some of our experienced users will get something out of this as well. So let's get started. So, like I said, a lot of great content. We are going to go over load cell design and how they work, capacities, models, how to choose the right load cell. There are so many different load cells. Usually there's more than one that will work for each application, but we're going to go over the considerations on how to select the best one. We'll talk about factors that impact sensor accuracy, some of the things that interface does that some of the competition does not, leading to our superior performance, moment compensation, creep, eccentric load sensitivity. We'll go over calibration and troubleshooting, couple use cases, and some frequently asked questions. So, how do load cells work? Well, essentially, a load cell is measuring deflection. A load cell is a spring element made out of metal. There are strain gauges, very, very small resistors arranged in an electrical circuit we call a Wheatstone bridge, which I'll show you a picture of in the next slide. They are mounted on the load cell in such a way that when a load is applied, the strain gauges stretch or compress, and there's a change in resistance, and this effect is repeatable. So a certain amount of load equals a certain amount of strain equals a certain amount of signal that comes out of the load cell, specified as a millivolt per volt output. Strain gauges are basically variable resistors, which are glued to the surface of the load cell. They stretch or compress as a load is applied. They are wired in a Wheatstone bridge configuration, which allows you to apply voltage, which we call excitation, across the bridge and signal back to the instrument in millivolts per volt. So it can be a little bit overwhelming as there are so many. I will let Rob go over some of the considerations as to how to select the best load cell for the application.
Thanks. Yeah. So one of the things that we help interface in our markets, which is the UK, Ireland, and Turkey as well, we assist BIAS is selecting the load cells. And if you've ever held an interface catalog, you know it's several hundred pages long. There's so many options, different form factors, different connector options, mounting configurations, and so you can see interface load cells are pretty much broken up into the categories on screen here. We've got the low profile or pancake style load cells as they're known. We've got tension and compression variations. We've got compression only load cells. We've got load cells shaped in an S. We've got fatigue rated load cells for high cycle applications. Some of the load cells are quite small. Some of them are button shaped, as in a shirt button. Some of them are shear beam or bending beam load cells, and that refers to the way the load cell reacts to the force applied to it. We've got rod end canister load cells. There are load washers, which are load cells with a hole through the center. We've got calibration grade load cells for calibration applications, explosion proof or intrinsically safe load cells, which are safe for use in explosive environments, through hole, down hole, column, coil tubing, jumbos, all of these different options for load cells. So it can be quite overwhelming to choose the correct load cell for a specific application.
And I'll just jump in real quick. There are, if you look on the right side, these specialty load cells. Sometimes we will come up with a load cell specifically for an application, like our downhole load cell is really used in the oil and gas industry and is proprietary to interface. So if you have a challenging application, know that just because you don't see it in the catalog doesn't mean that we can't tackle it. We can develop load cells specifically for the need. Thanks, Rob.
Yeah, absolutely. And that's also the case for various options of these load cells. So you might find a standard load cell that then you need a specific option on. And if that's not readily available, that's something we look at retrofitting as well. Should we move to the next slide? There we go. All right, so interface load cell capacities range from 1 ounce or 10 grams up to 15 meganewtons, 10 grams being 0.1 newtons. And the accuracy can be as high as 0.02%. And that FS is for full scale. So that's 0.02%, sorry, of full scale output, which is really pretty good. Now, most interface load cells, or load cells in general, are ratiometric output in millivolts per volt of excitation. We can also fit internally amplified amplifiers to the load cells, which will give you control signals. The common ones are 4 to 20, plus minus 10, 0 to 10, etc. Another option would be environmentally sealed. So if you're in a humid or a wet environment, they're going to be used outdoors. You might seal the load cell to protect the internal components. Another very important consideration is the thermal compensation. So we can temperature compensate from minus 50 degrees Celsius to 200 degrees Celsius, depending on the application that's needed. There's also multiple bridges. So you could get a single axis load cell with multiple bridges for redundancy or for calibration or for control of a machine or system. You also get multi-axis load cells, which measure in, it's a single flexure that measures in 3 or 6 directions. And they will also have multiple bridges, multiple outputs. We can do explosion proof, as we mentioned before. CE compliant, ROSH compliant. Submersible, we do IP68 load cells for use in wave tanks or subsea applications. There's mechanical overload protection for some of the load cells, especially the smaller capacity, where we'll talk a bit more about overload later, I think, but you can physically stop the load cell from being overloaded. TEDS stands for Transducer Electronic Data Sheet, and it's a small chip that can be fitted to the connector of the load cell or in the cable somewhere, and it holds the calibration data for the load cell. The data is held in an IEEE standard, and if you've got a TEDS compatible indicator electronics, it can read the data on that chip and scale the electronics specifically for that load cell's calibration data. We also do customer specified electrical and mechanical connections. So if you've got something specific that you require, we can generally look into that, supply that factory fitted. The calibration certificates can also be modified. We could do specific runs or specific points or specific temperature compensation, as we already mentioned, and proof loading as well. Interface manufacture their own strain gauges. It's one of the things that's unique about Interface. That allows us to have greater consistency across various batches rather than if we bought them in. And also a higher output, higher signal to noise ratio. And this is from a historical standpoint as well. Interface strain gauges were far ahead of the competition. And we still find a lot of benefits to manufacturing our own gauges in-house. Next slide. Right, so as far as choosing the right load cell, there's a lot of important considerations. So the first question that would normally be asked would be the capacity. How big is the force that you need to measure? Most people will know that. But then there's also mechanical considerations, dimensions, mounting. Is it going to be threaded? Is it going to be a load button? Are they going to be rod-end bearings? We could also consider the size of the load cell. Will it fit into the system where it's being placed? Sometimes for the force that you need to measure, a very large load cell would be required and may not fit into a specific system. So we could look at a different form factor, like a column load cell, which would be longer and thinner, but still take a very high load. The electrical output needs to be considered. Can you take a millivolt per volt reading with your electronics? Or do your electronics only take 0 to 10 volts? As we mentioned before, we can then provide an amplifier that matches that output. One isn't really better than the other. 5 volts isn't better or worse than 10 volts in terms of output. But one of the things you should consider is long cable runs or noisy environments. We tend to use 4 to 20 milliamps for those, just because they're more resilient to noisy environments. The other thing that's very important to consider is temperature and moisture. Moisture or inside the load cell can lead to corrosion on the flexure or on the gauges, which is obviously not what we want. So if there's a humid or a wet environment, we would definitely need to seal the load cell. So temperature ranges, most load cells are used in a lab environment, so room temperature is fine, but occasionally there need to be temperature varied environment, like an oven or in an application where they're exposed to heat from engines or something like that. We could then temperature compensate for a specific temperature range, so that would need to be discussed. We can also talk about things like pressured environments, so in vacuums or in high pressures, we might need to do a vented load cell, so that the internal cavity is not applying load to the flexure due to the pressure variance. And the last thing we need to look at is the accuracy. performance of the load cell. Obviously, the higher the performance, the more accurate the load cell, the more expensive it is. So it's not always required that some applications go for the highest accuracy load cells, so it would just be above and beyond what we needed. So yeah, we need to match the output and the performance of the load cell to the specific application.
Yeah, very good, Robin. I'll just jump in real quick. I think just providing the full picture of the application is always important when engaging an application engineer or speaking with UK or with BIAS. You know, we send load cells into space. We send them deep into the earth. Just knowing exactly where they're going to go is always helpful in avoiding any potential problems in the future. A lot of times, bits and pieces of the application come in, and by the time we're ready to produce something, another piece of information will come in at the last moment sometimes, whether it be how it's being mounted or where it's actually going to be used or the number of cycles. And then it's kind of back to the drawing board, which could hurt, you know, delivering on time. But all of these considerations are very important when selecting the best load cell.
Yeah, absolutely. So when we're talking about the capacity of load cells, there's the working range, and there's an overload range, and then there's an overloaded load cell. And most interface load cells have an safe overload capacity of 150%. And what that means is if it's a 100 Newton load cell, you're safe to use up to 150% or 150 Newtons. And past that point, permanent damage occurs. So the flexure is permanently deformed. It's irreparable most of the time. And you will be looking at replacing the load cell. That 50% overload capacity is meant to be used for unforeseen events. So things like the actuator locking up or something breaking in the system and overloading the load cell. The load cell needs to be able to survive these unforeseen events. So the working range, we try not to go over that working range at all. But you do have 50% headroom, which definitely helps. And some customers do use that 50% headroom as part of their measuring range. There's several disadvantages to doing that. The primary being that we're not sure exactly of the output and the errors associated with going over the range. So unless it's calibrated over range, you can't be sure of the errors that are involved. And the other is that you eat into the fatigue life of the load cell. So it starts getting damaged over time. Yeah, so the working range is where you want to have most of your load being taken up. Next slide. So with mechanical mounting, most of the critical aspects, it is one of the most critical aspects, sorry, of mounting your load cell and of accuracy. Off-axis loads can produce very, very high errors, much higher than most other things like temperature or even the performance of the load cell. And it's a great thing to discuss with the application engineer how the load will be introduced, be it clevis or threaded rods or rod ends or domed surface for a button or adhesive, or there's very many options. So knowing that in advance will help us specify the right load cell for your application. Continuing on from that mounting, actually, one of the very key things is the flatness of the surface. If you're mounting the load cell not through the threads on the base, for example, you can see the load profile on the right there doesn't have a base on it. We would need to provide a surface that is very similar to the base. And the base that is supplied with these load profiles is very flat. It's also very hard, and it's matched to the same material as the load cell. So if you were to mount a steel load cell onto an aluminium base, then vary the temperature, the change across the different materials could apply a load, it could introduce errors that are obviously undesirable. So you need to consider the mounting surfaces involved when applying loads onto these load cells. It's also recommended that they're hard because obviously if they're deformed, that's taking deformation away from the flexure, which introduces error as well. It's good practice to apply the bolts on a base in a similar way that you would to lug nuts on a wheel on the car. You go in a star-shaped pattern and incrementally apply torque just so that it's evenly applied across the radial edge of the load cell. Thing I missed over there is that the base should be thick enough as well, because if it's too thin, it ends up bending or deforming, which then also introduces errors. Eccentric or extraneous loads. You can see there we're talking about moment loads or torsion or side loads on the load cell. It's very important that the load cells are loaded through their primary axis. That's where they're calibrated. That's where there's going to be the least amount of error. But also, if you apply high moments or high side loads, you may overload the load cell inadvertently. So even though you're only applying, in this case, it's a 1,000-pound force load cell in the picture. So you're applying 1,000 pounds force and you're applying 1,000 pounds force side load, you may damage the load cell that way, even though you're not specifically overloading it on the primary axis. So it is something to be very aware of, and it's something that causes a lot of errors in a lot of systems. So it needs to be accounted for. Then we're talking about electrical signals. So as I mentioned before, most load cells are millivolt per volt output, so ratiometric, depending on the excitation voltage. But as I said, we can provide electronics either in the form of displays and amplifiers, supplying the load cell, or internal amplifiers. And that's just very much dependent on the system that you're using. You need to see the values in front of you on a screen. You need to record the values on your laptop via USB, or do you need control outputs, that kind of thing. Those are all good to know, good to speak with your application engineer about. Noise, as I mentioned before, is a consideration. The cable length. Do you want 4-wire connection or 6-wire to have sense? One of the great things about sense wiring is that you could have longer cables and mitigate the effects of the cable resistance on a long run by using the sense wiring configuration. The load cell needs to be sense wiring capable, and the electronics needs to have that capability as well. Another important consideration is grounding. You get grounding loops or noisy environments. The proper grounding is imperative, otherwise it eats into your usable signal and can expose you to errors as well. There you can see two examples. The top one is an S-type load cell. That is an unsealed load cell. Most of the time, unsealed is actually better than sealed for most applications, and that's just because you've got all of the load going through the flexure and therefore through the strain gauges. As soon as you seal it, you've got external load paths that the load can travel on, which can introduce errors if you're not careful. So that needs to be carefully considered when selecting a load cell for your application. Obviously, if it's going to be a noisy and humid or a hot environment, or there's going to be corrosive materials or something like that, we would need to seal the load cell. And that's where you can see the bottom one. That's a fully hermetically welded stainless steel load cell. So it's IP68 sealed. It's also ATEX, I believe. We use IP ratings to verify how well sealed the load cells are. That's kind of industry standard. And it's worth mentioning as well that some form factors, some types of load cells cannot be sealed at all just due to their nature. And also, depending on the environment, you need to take a look at the cable that you're selecting. The sheath of the cable needs to be resistant to fluids or temperatures that it might be exposed to. So if it's a very high temperature environment, you would need a high temperature cable, or if it's exposed to corrosive material, again, you need material sheath that is resistant to whichever corrosive material is in the application. We also do environmental connectors that are sealed by IP68, mil spec, or whatever is required there as well. I think I'm going to hand over to Jeff now to talk about the factors that impact sensor accuracy. And yeah, go ahead, Jeff.
All right. So what major factors impact sensor accuracy in testing applications? So a few considerations here. So the specifications, every data sheet, every load cell is going to come with a data sheet that's going to give you all kinds of specifications. We'll go over some calibration procedures, why cables are important, Rob touched on a little bit, and then instrumentation scaling. So first thing is, yeah, you won't find an actual accuracy value on the data sheet because some of these specifications may not matter in your application. Each data sheet will have a list of specifications, nothing that says accuracy. You will have a table of specs. You cannot just pick one to determine the accuracy. And like I said, some of these specifications may not actually apply when assessing your application. When you discuss what you are trying to achieve, we can kind of hone in on the specifications that will be most important regarding your application. You will notice different units, percent of full scale, which is the full calibrated range, percent of rated output, which is the percentage of output capacity, percent is a percentage of reading, and then a percentage of degree, and then some are time related. So these are two of the big ones that we talk about a lot: nonlinearity. So nonlinearity in hysteresis are very common. When you load a load cell, it is not perfectly linear. There is a bit of a curve. How much of a curve is there? And that is the difference in output from a straight line. And hysteresis is when the load is removed. So the difference in ascending versus descending curves. This is a good example of a spec you might not care about if you're not taking into consideration any descending data points. The hysteresis may not be all that important to you. But if you want to take a point on the way up and the way down, then you need to know. We do offer special calibrations around the points that you are loading to reduce these errors if necessary. So static error band. So a band encompassing all points on the ascending and descending curves centered on the best fit, line of best fit, expressed in percent of full scale. So the static error band takes into account nonlinearity, hysteresis, and non-return to zero. If you fit a best fit line straight through the data and fit a band in and below the data, that is your static error band. It is the output at capacity at this straight line. So we suggest you use this when scaling instrumentation. So non-repeatability, that is the maximum difference between output readings for repeated load under identical loading and environmental conditions. It is an interesting specification. In practice, it is quite difficult to achieve, to exactly identify or to load exactly identical conditions. So the non-repeatable specs can be quite good in a load cell or a system, but it is usually not the case. It is expressed in percent of rated output, so the declared capacity of the load cell. So calibration. Calibration always has an uncertainty. It doesn't matter how great the load cell is, how certain are we of the loads applied? If we're using a hydraulic calibration rig, was it really 1,000 pounds or was it 1,010 pounds? What is the uncertainty of the load applied? If you're interested in measurements at the lower or higher limits of the load cell, you might have interesting or unique mechanical connections. We can calibrate in situ to calibrate those variables out of the load cell. ASTM E74 multi-run with lower load limits. This would be a multi-run used to calibrate load cells that are used to calibrate load cells. So if you have, say, our Gold Series 1600, we would perform an E74 calibration on this load cell provided to you in order to calibrate load cells for your application. So Rob touched on. Oh, go ahead.
Sorry, the ASTM E74 is very similar to an ISO 376 calibration in terms of multi-run lower limits. There are some key differences, but that is also something we can provide, or either an in-house ISO 376 calibration with interface or with an external lab prior to shipping out to you. So if that's something you require rather than E74, it's something you should discuss, and we could look into as well.
Thanks, Rob. So cable lengths. When a load cell is manufactured with a certain cable length, the length is taken into consideration when it is calibrated, to the best of our knowledge. Sometimes people like to add cable length. If you add 100 feet of cable, it can cause significant errors. There could be drop in excitation voltage. It depends on the gauge of wire. Thicker, fatter cable is better. More so when extreme temperatures are introduced. Sense wire is the additional 2 wires that Rob touched on that can be added, which can take into account and correct the amount of signal at the load cell. So Rob did touch on the sense wires. Like I said, if your cable run is longer than what is typically found in the field, these sense wires, and it has certainly helped solve some issues that we've seen, unexpected errors, and really what it is every load cell cable has always at least 4 wires, excitation plus and negative, signal plus and negative, and then we add these 2 sense wires, and it will read the excitation at the load cell and provide that information back to the instrumentation. The instrumentation can scale that correctly, provide greater excitation, which will allow the load cell to cut up that signal and provide that back to the instrument. High-level signals typically are not affected, so milliamp and voltage signals are typically not affected at reasonable cable lengths. Instrumentation scaling. So the measurement is only as good as your instrument. You can adjust your instrument if it is not reading correctly. So how do you adjust the instrument? You can apply a load to the load cell when it is attached to the instrument to scale the load cell accordingly. You can also use a millivolt per volt output that is listed on the calibration certificate. If you dial up a specific millivolt per volt and say it is equal to 100 pounds, for example. Shunt calibration is similar to using a load cell simulator. The shunt resistor can induce an output signal that can be used to scale your instrument. If you have a non-linear system, you can use the instrument to apply linearization to the data using multi-point calibration. And then Rob touched on TEDS earlier. Essentially, it's just a chip that is within the load cell, and it's kind of plug and play. So as long as your load cell is TEDS ready and your instrument is TEDS ready, the instrument can read the information from the load cell, serial number, capacity, output. Certain instruments can read the data and self-scale. The instrument will figure out what load cell it is, what load cell is attached to it. So it's really good if you have multiple load cells. You can plug and play and switch them out without having to do any scaling at the instrument. So now I'll let Rob talk about performance, moment compensation, creep, and eccentric loading, and some of the things that we do at Interface that some of our competitors do not.
Thank you. So we mentioned eccentric and side loads before. So the definition is any load that's not applied in the primary axis, so through the threads in the center of the load cell. The design of the interface load profile is specifically set up to be very insensitive to off-axis loads. So the load profiles specifically deal very well with small moments or small side loads. And that is a really great feature of them, and not a lot of competitors can do that. But some interface load cells, such as an S-beam or mini beams, are not very good with eccentric loads. So depending on the form factor of your load cell, you need to take into account these eccentric loads on a varied scale. And these eccentric loads can be found in most applications. They need to be checked because they can be the single greatest source of error in the system, up to 10 or 15% even in some cases. And when you're talking about a 0.02% error on the load cell performance, you then introduce a 10% error due to an off-axis load, and the performance of the load cell goes out the window. So it's a very important consideration. So on the next slide, we'll see Interface actually do moment compensation on the load profiles. Big on the right there is an off-axis load application. So there's a weight on an arm which applies the bending moment to the load cell. Through a very manual and iterative process, the off-axis load is applied, and then adjustments are made to the load cell output, and they're applied. So that arm swings around 360 degrees and applies that off-axis load at various points. Adjustments are made, recorded, more load is applied, adjustments are made, and so on, until there's a very tight spec, until it meets the spec on the data sheet. So one of the key things about that is all of the data points are recorded and stored, so it's fully traceable. So if ever you wanted to see the moment compensation data for a specific load cell, for your specific load cell, you could ask us for that, and we should be able to supply it for you.
And if you know where these eccentric loads might be coming from, at least what angle, we can actually provide you a diagram and show you where the best compensation is at what off-axis angle. We'll actually provide a diagram and show you how maybe if you know where those loads are going to come from, you can install it appropriately and provide the best performance as well.
That's a good point. One of the great things about understanding all of this moment compensation is that it can be characterized, and you can see there we've got some data on the performance of the load cells at different off-axis loads. You can see the maximum error is very small, somewhere between 0.05% and 0.1%. So that's far above what most of the interface competitors can do with their load cells and off-axis performance. But if you're expecting off-axis loads, it's definitely something you should talk to your application engineer about. It's something that needs to be considered when choosing the form factor of the load cell. So the capacity, because if your off-axis load is large enough, it might overload the load cell, so you might have to go for a higher capacity load than what's going through the primary axis, as I mentioned before. But it is definitely a very important aspect. Here you can see some of the calculations we can do for composite loading. So that's loading in the primary axis as well as off-axis loads or moments, torques. So we won't go into too much detail here as load cell basics, but if you did need to discuss composite loading with your application engineer, they are equipped to talk about that. And as Jeff mentioned, to recommend an angle of mounting or a specific type of load cell that can best deal with the loading parameters in your application. Right, temperature compensation. So all of the interface load profiles and a lot of the other load cells are temperature compensated. So we've got a graph on the right-hand side here of an uncompensated load cell. That's the first curve. So you can see as the temperature goes up, zero balance changes dramatically. And then we've got the second curve being load cell that's temperature compensated at room temperature and at a high up temperature. And lastly, we've got the third line there, which is what interfaces do. They temperature compensate at a cold temperature and hot temperature. And what that does is it flattens out the curve right at the room temperature level. So you've got your best performance at that room temperature. So as I mentioned before, most load cells are used in a lab environment or a room temperature environment. So that's desirable to have the flattest part of the curve at room temperature. So if you've got a 5 or 10 degree variance in your lab temperature, you see a very, very small effect on the load cell output. As always, if you've got an application with a specific temperature range, you need that compensated temperature to be 70 degrees Celsius instead of 25 or 20, whatever room temperature. We can adjust that temperature compensation to give you the best results at the temperature your load cell is going to be used at. There have been some extreme examples of this working inside engine cells, for example, in jet engines. I mean, very high temperature applications where we can temperature compensate at those temperatures, and the same for low temperatures. So it's just about us knowing what you need and being aware that this is something we can do, and then basically doing that for you.
Yeah, that's a good point. Every load cell we compensate at zero at different temperatures, but we do have another temperature chamber where we can calibrate your span at a specific temperature within a little bit tighter of a range. But yeah, like Rob said, let us know where these are going to be used, and if you want us to calibrate the span at a specific temperature, we'll do our best to accommodate those requests as well.
Okay. Now you can see different load cells have different specs there, percentage change of rated output per degree. Obviously, we would use Celsius. But yeah, so we just need to be aware of what you're looking for to be able to specify the correct load cell. Next slide. Yeah. So I think lastly on this topic is creep. Creep is defined as a change in output over time. So if you load your 100 Newton load cell to 100 Newtons and your indicator says 100 Newtons, as long as the temperature and the load stays the same, you come back in an hour's time and it reads 101 Newtons, that's probably creep. Load cells and all force measurement flexures have creep in them, and creep never stops. One of the key things about creep is that it happens very early on. So most of the creep happens in the early seconds, or the first couple of minutes at maximum. And then it kind of tapers off, or the effect of it tapers off over time. You can see on this the semi-log graph we've got here, the change in creep in the first 10 seconds is the same as the change in the next 10 hours is the same in the next 10 years. So the effect, it flat lines over time like that. It's also symmetric and repeatable. So if you apply the load, the creep happens very early on, and then when you take the load off, the creep happens early on the way down as well. So it will go back to zero and then slowly settle to where it came from. So interface 100% creep tests all of the mini products, especially. It's a key thing to look at in the data sheet for your load cell as well. So I'm going to hand over to Jeff to talk about calibration and troubleshooting.
All right, so calibration and troubleshooting. So all load cells should be calibrated and certified. Every load cell that leaves the factory will be calibrated, at least 5 points up and 1 point down. And again, we discussed some of the other calibrations that we can offer. Calibration is recommended every 1 to 2 years. It also depends on usage. Feel free to send these back to interface to be calibrated, or we do offer gold standard calibration load cells that could be used to calibrate the load cells, in your application. Take a look at our website. We have troubleshooting guides, online guides. We have load cell books. We have white papers. We have technical services. Right on the website, you can see some of the contributing factors to load cell accuracy. It goes in a little bit more depth than what we've covered in the presentation, but a lot of good information on the website. Wanted to touch on multi-axis sensors. They are becoming more and more popular. As Rob was talking about earlier, when we talk about eccentric loads, a lot of times that is going to cause errors in your application that won't be seen. Now, as much, Interface does a lot to make our load cells insensitive to eccentric errors. However, we cannot be sure that they won't be introduced. So although our load cells are relatively insensitive, if those eccentric loads are there and they cause overload, it could be the case that we're damaging load cells and never know about it. So these multi-axis sensors will give us the information that might be needed. So why do we use them? 3 or 6 axis load cells. More data. So multi-axis sensors provide more information. We can offer 2, 3, and 6 axis sensors. Our 2A load cells will measure axial and torsion force. Our 3A load cells will measure all of your forces simultaneously in 3 mutually perpendicular axes, your X, Y, and Z. And your 6 axis will measure the same 3 forces as well as the torque or moment about the 3 axes. So if you're already investing all of these dollars into your application, you might as well maximize your return on investment. Sometimes if you know that you need multiple measurements, it could be a lot. It actually could reduce your cost from purchasing multiple single axis load cells, and it could be much easier to mount than trying to configure multiple load cells in an application. These load cells are becoming more and more popular, like I said. They're ideal for industrial and scientific applications such as aerospace, robotics, automotive, and medical research. Getting a little bit more into detail, there's a 36-term coefficient matrix, which is included for calculating the load and torque of values in each axis. And I will touch on an 8-channel amplifier USB PC interface that is also available, which simplifies the data analysis. So here's a few pictures of multi-axis load cells. Just kind of get you an idea of what these look like. They are gauged all independently. So if you were to cut one of these open, you're going to see bridges measuring in all directions. Capacities anywhere from 2 newtons to 500,000 newtons. Low height, compact size, low crosstalk. And crosstalk is making sure that if I have an axial load, I'm not seeing any side loads or moment loads. So the way that these are manufactured, very, very small, minimal crosstalk. So what do we do with all this information? We need an instrument that is able to take this in and give us usable data. So the instrument that we recommend using to pair with your 6-axis load cells is the BX8. So it does have 8 channels. 2 channels can be used for other sensors, whatever might else be going on in your application. It will do the internal calculations that run across the coefficient matrix, active scaling of analog outputs according to internal calculations, multiple outputs if you're going to another data acquisition. This is an important one, 48,000 samples per second per channel. So each one of these channels is sampling at a very high rate and all at the same time. Very easy integration to a PC using USB, and then of course we're going to give you all the graphing, logging software, and the ability to analyze the data. So here's a kind of a common app. Well, robot arms have been a very common application. All kinds of moment and torque that we want to be measuring to be sure that we're not overloading the load cell itself or any of the other mechanical mounting considerations that are used in the application. But this is a bit unique where we have 4 multi-axis load cells kind of sandwiched in between 2 plates. We call it a force plate. So reaction loads at the machine base does require 12 channels of instrumentation, so a lot of data coming in. But a force plate is a system with multiple multi-axis sensors mounted between 2 plates, larger capacities than a single 6-axis. It's able to react to high moments. The results dependent on the characteristics of the plates and other system components, and they can be difficult to calibrate. And a lot of times, you know, these will be calibrated once they're installed. So an in situ calibration a lot of times is going to be best. And you know, sometimes there's not. You know, it's easy to calibrate a low profile load cell using one of our hydraulic presses, something like this. We may need to partner to figure out exactly how to apply the loads to a force plate like this. Some use cases. So using a WMC stainless steel mini load cell, we had a customer come to us with a pharmaceutical application, so a pill press machine. It was important for the load cell to be small in size so that it could fit in the machine, and needed to be able to be cleaned because we're making pills for human consumption. We paired it with one of our handheld indicators. The customer can apply the load, measure it, make sure it is within their certain parameters, put it away, and be confident that they are manufacturing correctly. Also, the WMC is a washdown load cell, so if between cleaning, it will hold up to any kind of moisture and other environmental considerations.
This is a medical application where a customer wanted to fatigue test some prosthetic limbs. They also wanted to test them at high loads for lack of fall or some unexpected usage on the prosthetic. So we recommended an SSMF. The F stands for fatigue rated, and that allowed them to apply a high cycle load at low loads, and also measure higher loads at a shorter cycle time. So it was a great solution for them. They paired that with a 9890 indicator, which is a display indicator. It displays newtons on the screen. Also provides with a control signal so they could control their hydraulic actuator's force, and then also USB to scale the indicator and analyze the data, etc. So that was quite an interesting application. So we did a little while ago.
So next, customer was looking to make sure that their load cell was in good working order for an upcoming test. So low profile load cells are very good when there may be bending moments or misalignment. Customer had load cells in multiple machines with multiple load cells you might start having issues. Well, what do you do? First thing might be to check the load cell. So using, let's see. So using one of our gold standard load cells, we were able to essentially calibrate or check the load cell that was going to be used in the application. So pull out the load cell, put it into the apparatus here, measure the load cell. If it's doing what you expect to do, great. Put the load cell back in and continue your troubleshooting elsewhere. If you're receiving measurements that aren't desirable, that might be time to ship the load cell back to interface, let us calibrate, and do any type of troubleshooting that we might need to do in the rig. So some frequently asked questions. Why do we make our own strain gauges? So we make, well, first thing that we do is actually not only do we make our own strain gauges, our manufacturing is totally vertically integrated. So we start with the steel, we cut it ourselves, we gauge it, we wire it, we can it, we calibrate it. And having full control of the strain gauge, which is a very key component to the sensor, we're able to match the material of the strain gauge to the material of the load cell, which allows for better temperature performance. We don't use compensation resistors. Those add complexity and more failure points, higher output because you don't have the resistors changing temperature that might not be bonded well to the metal. What type of temperature testing do you do? So we touched on this a little bit earlier. We compensate to the best about room temperature. If you want something different, please provide, and we will be glad to accommodate. And I'll let Rob kind of touch on, some of the finer details here.
Sure. Yeah, this is a great image of a cutaway of a low-profile load cell, so you can see some of the complex machining that goes on in making one of these. So the great thing about Interface's in-house machining is that, everything's under control, everything's quality controlled in-house. Means a lot of consistency across different load cell types. So you can see there we've got moment compensation during production. So the way the flexure is shaped, moment compensates naturally. If they are fatigue-rated load cells, they're truly fatigued. So we talk about hundreds of millions of cycles fully reversed, so all the way from full-scale tension to full-scale compression. We also have control of the specifications and what materials get used, what gauges are chosen for a specific load cell's performance. So we can have class-leading performance there. The threads that we use are high quality, so you can specify, but we do some standard, very high quality coarse and fine threads depending on what's needed. And yeah, it's just overall a fantastic product.
So to summarize, why interface load cells? We do guarantee our load cells will outperform our competitors. We have an integrated manufacturing process. Nothing is outsourced. Like I said, we machine it from the blank all the way to the final product. Temperature compensation is done by actually kind of touching on this. How do we actually do that? Temperature compensation is done by adding wire to the circuit that has the opposite resistance change to the circuit. Some of the other things that we can do, send out vented diaphragms to handle different pressures. There's just a lot of things that we do. Like I said, when you are developing an application, bring us in. I would say 30% of the load cells that we send out are somewhat custom. It might be as simple as a different cable length, calibrating it at a different point. But we also get into some of the very special load cells, like the downhole load cell, that was engineered for a specific customer. And then we did such a good job, we decided to make it a standard product. We also get into what we call AGT, assemble, gauge, and test. So if you have an application where a torque transducer or load cell is not going to fit in physically, or for whatever any other reason, what you might find in the catalog is not going to solve your problem, know that we can take, you know, a piece of your application, actually gauge it, transducerize it, and turn that into a force measurement solution. So a lot of the things that we do, I think, set us apart from the competition, and also, you know, I hope that we make it easy to work with as well, and know that we don't want to just take orders from the book. Bring us your challenging applications, and we're more than happy to engineer a product specifically for your application. So that is the end of the presentation. I think I saw a couple questions come in. Looks like they might have been addressed, but Ulyss, I'll hand it back to you.
Yeah. Okay. Thank you for your presentation, both of you. Let's move on to question and answer session, right? Hakan Bey had a question. We will interest this case. We can check your load cell in our test center. We will contact with you about it in this week. And one of our guests had a question. Who wants to answer it? Can you see?
Yes, the one about the load pin. So the way I understand that is load pins are a bit unique in that the environment that they're installed in, generally, they're free to rotate, actually. And the alignment is obviously, as we've discussed, very important in the load cell. So if you're talking about a load pin, what we would do is manufacture a keyway or some kind of feature on the head of the load pin or on the base of it, where we could put an anti-rotation feature so that it locks in a repeatable orientation, actually, so that the load is always going through the sensitive axis of the load pin. So that's something we need to discuss in more detail with drawings and things, but it definitely can be done. We've done load pins in the past, and they've been very successful.
Thank you. And one of our guests has a question about the new force plate.
Does the new force plate have control hardware? How's it working in synchrony with 12 sensors? So we still use our BX8, but we'll just be using 2 of them. The first BX8 will take in, you know, the 8 channels, and then we'll use 4 for the other. They will talk to each other. You can kind of daisy chain them together, and then connect that into the PC, and the PC will accept all 12 channels in synchrony. And like I said, we can log that. We can graph that, and then the BlueDAC software will analyze all that data and give you, usable output.
Yeah. Is there anybody has a question anymore? We can wait. Yeah. Okay. It seems the presentation includes all questions. Okay, thank you. We would like to thank you all the participants again for their time. I think we refreshed our knowledge and learned some new details today. If you would like to attend our another webinars, you can follow our LinkedIn page we are planning to organize the second of our webinar series with Interface Company in the following months. The second webinar will be about the torque sensors, torque transducers. And of course, you can contact with us anytime you want to discuss and ask something about interface products anytime. So have a good day, all of you. Hope to see you again. Thank you. Bye bye. We can finish.